Let's talk about continuity. So, I'm sure you all have at least an informal definition for yourselves of what continuity means. And informally, you're just thinking that a function is continuous if you can draw the whole thing without ever picking up your pencil, if there's no interruptions in it. So, interruptions in functions would be things like holes or vertical asymptotes typically. Now, the more formal definition of a continuity is described right here. So we have to meet three different conditions in order for a function to be considered continuous at a point C. All right, so the first condition is that f of c is defined. Second condition is that the limit at c exists. And the third condition is that the limit has to equal the value of the function. Right? So this is just telling us about continuity at a particular point. But of course, if you can prove that a function is continuous at every single point, then the function is continuous everywhere. So I want to show you a couple different types of discontinuities that can happen in a graph. And we're going to differentiate between what's called a removable discontinuity and a non-removable discontinuity. We're always just going to be looking for these on an interval from A to B. All right, so first way that you might have a removable discontinuity is if you have a function that just has some sort of hole in it. Okay, this is considered a removable discontinuity. And the basic idea here is that our function, it goes right up to that discontinuity, hops over it at the hole, and just keeps on moving. The reason this is considered removable is because you could theoretically fill in the hole. All right, second type of removable discontinuity is actually also another type of hole. Let's say we have something like this. Except this time you also have your function defined at a different value for that. Let me call this x value right here c. Let me do the same on the previous example. All right, so at c in this case, we have a hole, but then we also have our function defined elsewhere. Again, this is considered a removable discontinuity because you could theoretically redefine this point to fill in the hole. All right, now non-removable discontinuities, there's two different ways that these can happen. The first way is with some sort of vertical asymptote. So say we have a function that looks maybe something like that. So you have that vertical asymptote in there at x equals c. That's non-removable because you can't just redefine the function in order to make it continuous. There's no hole to fill in. No matter what, that's always going to have a discontinuity at c. The other type of non-removable discontinuity is if we have some sort of jump in our graph. Let's say something maybe like that, where it jumps from one point down to another. Again, this is non-removable because you can't just fill in the hole and make it continuous. There's nothing you can do to redefine that function to make it a continuous function. Okay, so these are our different types of discontinuities. Let's go ahead and look at these graphs right here, and let's think about what types of discontinuities they have, if any. All right, so our first function we have here is some sort of cosine function. And we can, of course, just see that it's just going to keep oscillating back and forth. So there's no holes, there's no asymptotes, there's no jumps. So this one is actually continuous everywhere. This one has no discontinuities in it. Okay. Our second one, let me blow this up a little bit so you can see that a little bit better there. So this graph, you can see we have this hole and then we have this point right above it. So because we have that hole in the graph, this one has a removable discontinuity. at that value of the whole, so at x equals -3. Right? And again, this is considered removable because you could theoretically redefine your function to take this point and fill in the hole. We'll look at an example of that in a few minutes. All right, our next one here, we can see that this time we have this vertical asymptote at x equals -5. So that's going to be an example of a non-removable discontinuity. And that's, of course, at x equals -5, where we have that vertical asymptote. All right, and lastly here, we have our function looks linear, we've got a hole, and then it jumps to this more quadratic type function. So because we have this gap right here, this is a non-removable discontinuity. And that's going to be at x equals -3. Okay, so those are our different types of discontinuities that we have. Let's go ahead and look at a few different equations and try and figure out from the equation where our function is continuous. All right, so our first one here, we have f of x equals 1 over x, so we're looking at a rational function, which we know rational functions always have the potential for vertical asymptotes or holes. So we need to sort of see what's happening with this one. In this case, we have a larger degree in the denominator, which means we're going to have a horizontal asymptote at y equals 0. And because we have the x in the denominator, we also have a vertical asymptote at x equals 0. So quick sketch of our graph over here. Vertical asymptote at x equals 0, horizontal asymptote at y equals 0. And hopefully you remember generally what your 1 over x function looks like. It just has your two different branches in quadrant 1 and in quadrant 3. All right, so in this case, because it has a vertical asymptote at x equals 0, this is considered a non-removable discontinuity. All right. Now the question though asked us on which intervals is each function continuous. So the only place that it is discontinuous is at x equals 0, so it would be considered continuous everywhere else. So on -infinity to 0 and 0 to infinity. All right, next one here, we have another rational function. So I'm going to go ahead and factor this out to start with. Of course, our numerator is a difference of squares. So we can factor that out as x plus 1 and x minus 1, which when we do that, we can see that we have that common factor that cancels out, which will give us a hole in the graph at x equals 1. Go ahead and simplify this. So this would just simplify down to x plus 1, so no vertical asymptotes on this one. We would have the y coordinate of the hole then if we just plug our 1 back in at y equals 2. All right, so again, just sort of a quick sketch of this function over here. So x plus 1 is just a linear function. Just count my ones on my scale here to keep it simple. All right, and we have this hole at the point 1, 2. Our graph is going to look something like that. All right, so the only place that our function has a discontinuity is at x equals 1, so it's going to be continuous everywhere else. So it would be continuous on the intervals negative infinity to 1 union 1 to infinity. All right, next we have a piecewise function. So with our piecewise function, I'm going to think about what the two pieces are composed of. So the first equation that defines this function is linear. Well, if you think about a linear function, there's never going to be any asymptotes, there's never going to be any holes. So this piece of it itself would be continuous everywhere. Same goes for the second piece, x squared plus 1, that's just a parabola, which again, parabolas are also going to be continuous everywhere because there's no holes, there's no breaks, there's no asymptotes, nothing. So the only thing that we actually have to worry about is this transition, because you could potentially have a break in the graph where we switch from one equation over to the next. So I'm going to consider the limits on this one. I'm going to look at the limit as x approaches 0 from the left-hand side of f of x. So from the left, we'd be using the top equation because that's x is less than 0. And we can just use direct substitution. So 0 plus 1 is equal to 1. And then we can also find the limit as x approaches 0 from the right-hand side of f of x. That would be using the bottom equation. So 0 squared plus 1 is again equal to 1. All right, so what that's telling us then is that our function over here, if we sketch it out real quick, it's going to look something like this. So the first half of our graph, x plus 1, just linear, will look something like that. And we just found that the limit as x approaches 0 from the left is 1, so it ends right here at 0, 1. And then the second half of our graph is that parabola. And that's just going to look something like that, because again, we said the limit as x approaches 0 from the right-hand side is also 1. So in this case, our functions meet up right here. There's no holes, there's no breaks, so this is actually going to be continuous everywhere. That's continuous everywhere. All right, now the next one is also a piecewise function. So we're going to think about it in pretty much the same way that we did the previous example. So again, just looking at the two pieces, x plus 3 is a linear function, that's continuous everywhere. And 6 is also a linear function, so that's continuous everywhere. So the only place that we could potentially have a discontinuity is at 2, where we switch from one equation to the next. So let's again look at our limits from the left and the right of 2. Let's start with the limit as x approaches 2 from the left of f of x. So it's going to be using the top equation. So we would plug in 2 plus 3, and that would equal 5. So then if we look at the limit as x approaches 2 from the right-hand side of f of x, that's using the bottom equation, which is just always 6. So in this case, we're saying the limit from the left-hand side is different than the limit from the right-hand side, which would mean that the limit as x approaches 2 of f of x does not exist. So that's going to mean that our function is discontinuous at x equals 2. So let's go ahead and just sketch this out so we can see it visually. Counting my ones on my scale here. Okay, something like that. All right, so our first function, x plus 3. So y-intercept of 3 here. And it's switching at 2, we said. We have slope of 1. It's just going to look something like that, roughly. And then the second half of our graph is just y equals 6, which would just be a horizontal line going that way. All right, so we can see by graphing it out that of course we have this break right here. We have this gap, we have a jump from one equation to the other, which is giving us that non-removable discontinuity. That's at x equals 2. All right, so we would say then that it is continuous everywhere else. So on negative infinity to 2 and 2 to infinity. All right, one more piecewise function that I want to show you guys. So this one has 3 different equations that define it. So f of x is equal to x plus 1 when x is less than 1, 5 when x is equal to 1, and 4x minus 2 when x is greater than 1. So first thing I want to do is just sort of sketch it out and then see if we have any discontinuities and where. Again, just mark out my scale here. Let's count by ones. Okay, so we have 3 different pieces this time. So the first piece, x plus 1, when x is less than 1. So that's just going to be a linear function with a y-intercept of 1, and it goes up until x equals 1. So that first piece is going to look something like that. Then we have f of x is equal to 5 when x is equal to 1. So we'll have that point up there. And then we have f of x is equal to 4x minus 2 when x is greater than 1. So we're thinking about what that's going to look like at 1. So 4 times 1 would be 4, minus 2 would give us 2. So that would be right here. All right, so right where our other graph left off, that's got a slope of 4 then. So it's going to go 1, 2, 3, 4 up and look something like that. All right, so in this case, we can see that we have this hole right here, but we don't have any gaps or jumps. We just have a hole, and then we have this point up top. So this would be a removable discontinuity at x equals 1. Okay, so removable discontinuity at x equals 1, right, which is what part B was asking us for. All right, so then part C says, if we have a removable discontinuity, which we do, redefine the function to make it continuous. So if we think about our function here, we have this hole at the point 1, 2, and then we have this extra point up here at 5. But if we were just to take that point and stick it down here, then it would fill that in and we would get a continuous function. So all I'm going to do is I'm going to redefine this function to fill in that hole. So I'm still going to have x plus 1 when x is less than 1. And I'm still going to have 4x minus 2 when x is greater than 1. But instead of it being equal to 5 when x equals 1, I'm going to make it equal to 2 when x equals 1. Because again, that's going to take this point up here and instead put it right in that hole to make this a continuous function. All right, there's a few more examples again if you look at the notes that I posted, but that's where we're going to end the video today.